that Radix to DIT FFT for n equal to 8, and we start the computation from that general expression for DFT, which is given as x of k. If at all we say x of k, if at all we say that it's a DFT that is represented with k, which is given as summation n equals 0 to n minus 1 x of n e raised to minus j 2 pi nk on n is the general expression for computing the DFT. With n equal to 8, this can be rewritten as summation n equals 0 to 7 n minus 1, 0 to, if it is 8, x of n e raised to minus j 2 pi nk on 8 will be the expression when n equal to 8. And now the name itself says decimation in time, in the sense we are focusing on n factor and that cutting into pieces. Like we need to calculate, guys, we need to calculate x of 0, x of 1, x of 2, x of 3, x of 4, x of 5, x of 6 and x of 7. So these 8 samples, A is decimated into 4 samples, 4 samples, and that too even and odd samples, like x of 0, x of 2, x of 4, x of 6. This will form, this is cut, this is made as a one sequence, and another 8 is decimated into 2 fourths, and another sequence with x of 1, x of 3, x of 5, x of 7. This forms another sequence, like decimating in time, not the frequency factor, but we are decimating the time factor n. And 8 samples decimated into 4 samples and 4 samples. These 4 samples are still decimated into 2 samples each, and before doing that we need to rearrange this in bit reversal. Like if this is x of n, if this is x of n, if this is x of n, let this be f1 of n, and this part, this sequence, let that be f2 of n. And if I say, like from the 4-point DFT, if I want to pick up f1 of 0, it's picking up x of 0 from the 8-point DFT. That's the relationship between 4-point DFT and 8-point DFT. Like if I am picking f1 of 1 from the 4-point DFT, I am picking x of 2 from the 8-point DFT. f1 of 1, f1 of 2, f1 of 3. And even this one, considering this to be this sequence as f2 of n, this will be f2 of 0, f2 of 1, f2 of 2, f2 of 3. So representing the second sequence from the 8-point DFT, 4-point DFT and another 4-point DFT, still reducing, decimating this into 2-point DFTs. In the sense, what will be the bit reversal then? f1 of 0 from the 4-point DFT, I am picking x of 0 from the 8-point DFT. f1 of 2, I am picking up x of 4 from that one. Now these two, like decimating, 4 in 4, it is decimated into 2. Now these two will be forming. If I say, like if we represent this one with g f1 of n, let this be g11 of n. More precisely, g11 of 0, g11 of 1. 8 points decimated into 4 points, decimated into 2 points, and we are left with another 2 samples from this 4-point, and that one we're gonna have f1 of 1, which is x of 2, f1 of 3, which is x of 6. This one, another 2-point DFT, like it is g12 of 0, this is g12 of 1, and this one, even this is split into point DFTs. Once again with the bit reversal, if we say f2 of 0, we are picking x of 1 from the 8 point DFT, and if we are saying f2 of 2, it's a x of 5 from the 8 point DFT. Now these two will be forming these two point DFT, representing that as G21 of 0, this one, this is G21 of 1, and these two left over, we are left over with f2 of 1, which is x of 3, and f2 of 3, which is x of 7. These two will be forming another sequence with a 2 point, and this one representing this one as G22 of 0, this will be G22 of 1. So establishing this relationship, once we are done with this one, it's much easier for that obtaining that butterfly structure and cutting into that butterfly structure, drawing that butterfly structure. Guys, if we have x of n, we're gonna have x of k. If we have f of n, we're gonna have f1 of k. If we have g11 of n, we're gonna have g11 of k. The DFT of g11 of n will be g11 of k. Remember that one. That is very much important. And now we have to have that relation. Establishing that relationship is very much important while we break down that butterfly structure for n equal to 8. And now recalling this expression x of k, like we have 8 samples, splitting that into 2 fours with the even and odd samples each. How do we do that? Summation n equals 0, 1, 2, 3, and picking up the even samples, like x of 2n will pick up the even samples, e raised to minus j 2 pi, and n 2n will pick the even samples, k on 8. We are not focusing on this one, but we are focusing on the time factor n, plus summation n equals to 0, 1, 2, 3. We need to plug in the place of n, and we have to pick up odd samples. X of 2n plus 1 will give us the odd samples, e raised to minus j 2 pi 2n plus 1 k on 8. So guys, it has two parts over here, 2n plus 1, in the sense e raised to minus j 2 pi should be multiplied with this in this, and also e raised to minus j 2 pi 1 in k. We have two factors over here. Rewriting that one, how to rewrite? Let me rewrite over here and erase it later. E raised to minus j 2 pi, e raised to minus j 2 pi 2n into k on 8, for this into this on 8, into e raised to minus j 2 pi, e raised to minus j 2 pi into 1 into k on 8. And yeah, with this we have decimated that. In this one, it's a 4 point DFT, n equal to 4 samples, and even this one, 2 1s, 2 4s, it's a 4 point DFT. And what's the reason behind stressing it into 4 point DFT? To say that now this DFT is periodic with n equal to 4. That line has to be underlined and very much important in reducing the computation complexity in DIT FFT while drawing that butterfly structure. Even this one, we made, okay, we need to, I split this into 2 halves. This one I have rewritten over here. Even this one, it's a 4 times, like making it into 4 point DFT, stressing it that this sequence is also, this DFT is also periodic with n equal to 4. And so this part is a whole DFT with a k, and give us a name, giving it a name G11 of k from the first sequence G, which will be obtained from this one, f of k, the 4 f of k, which is obtained from this one. Let me explain while we go further. And even this part is a 4 point DFT. This one from here, this end, it's a 4 point DFT which is obtained from G12 of K. G12, this one, G12 of K, which gives like very much similar to this one. Where am I? Guys, not this one, not this one. We are still at 4-point DFT, isn't it? I'm sorry, we are still at this one. We didn't reach over here. I'm very sorry. I'm taking it back. It's a 4-point DFT. It's a K. It's a DFT, giving it the name F of K. If it is a DFT, some X of K, Z of K, it's in K. Plus, even this part is a 4-point DFT, F of K. Alright. So, to avoid confusion, giving the name F1 of K, saying that it's the DFT consisting of even samples from 8-point DFT, and F2 of K, saying that this picks the odd samples. This pick the odd samples and entire this one. What about this one then? It's a twiddle factor, guys. It's a twiddle factor. This one, it's a twiddle factor with the K on 8. It's a twiddle factor with the K on 8. We need to get back to this expression for computing the last stage of Radix to DIT FFT with n equal to 8. What is that expression? X of K. We need to get back to that X of K. X of K, which is F1 of K plus F2 of K with a twiddle factor K on 8, from which we're gonna get that X of 0, X of 1, etc., etc. to X of 7, making use of this one, which is decimated into 4, which is still decimated into 2. Now, the final 8-point DFT is obtained making use of 4-point DFTs, isn't it? And that 4-point DFT still can be obtained decimated into two 2-point DFTs, 8-point DFT, 2 4-point DFTs, 1 4-point DFT into 2 2-point DFTs. Now, how to obtain that F1 of K? F1 of K, it's a DFT. What is that? DFT of this one, F1 of n. X of K, X1, X of K from here, F of K from here, somehow related from, which is obtained from this one, F1 of K. Now, what is that? F1, how to calculate that DFT? It's summation n equals 0, 1, 2 and 3. Why 0, 1, 2 and 3? It's a 4-point DFT, so 4 samples. F1 of n e raised to minus j 2 pi 2n, I mean 2 pi. General expression for calculating the DFT, 2 pi minus j 2 pi n k, and n is 4. And it's a 4-point DFT, still can be separated into 2 sequences with the even and odd samples. That summation n equals 0 and 1, F1 of 2n e raised to minus j 2 pi 2n k on 4 plus summation. This one will be picking even samples. N equals 0, 1, F1 of 2n plus 1 e raised to minus j 2 pi 2n plus 1 k on 4. So this makes, and this no change in this one, n equals 0, 1, F1 of 2n e raised to minus j 2 pi. Now this we have decimated into 2-point. It's a 2-point DFT. Minus j nk on 2 plus summation n equals 0, 1, F1 of 2n plus 1, which picks odd samples from 4-point DFT e raised to minus j 2 pi 2n k on 4 into e raised to minus j 2 pi k on 4, isn't it? And guys, it's a 2-point. Once again, this one, it's a 1 times and 2s. It's a 2-point DFT. It's a 2-point DFT. Even this is a 2-point DFT. Even this is a 2-point DFT, and 2-point DFT, this one obtained from G11 of n. So F1 of K will be G11 of K plus G12 of k, odd samples, F1 and F3, F1 of 1, F1 of 3 odd samples of this part, and F1 of 0, F1 of 2 are even samples from here, G11 of k from here, G12 of k from G12 of n. That's what. And what about this one? This is a twiddle factor. This is a twiddle factor. It's a twiddle factor with a k on 4. Yeah, remember this one? This is 2-point DFT, n equal to 2, which is periodic with n equal to 2. Even this one is a 2-point DFT, which is periodic with n equal to 2. Now F1 of k is obtained from this one, this part. All right. So we need to get back to this one. F1 of k will be obtained from G11 of k plus G12 of k with the twiddle factor, k on 4, So that's one. In the same way, guys, F2 of k, which we have over here, F2 of k will be obtained from G21 of k, from this one, G21 of n plus G22 of k, same with a twiddle factor k on 4, similar to this one. So we need to get back to this equation for the last stage, and we need to get back to this one for the second stage. This gives the second stage and this gives the third stage of computation. We need to get back to that one. And remember, periodicity property is very much important in all these computations. Yeah, we'll have to reduce the computational complexity, and to do that we will be making use of the periodicity property. And what did we do? Yeah, we need to start with x of 0 and x of 4. All right, where do we have that x of 0? Yeah, we're gonna have that x of 0 and x of 4 with this one, x of 2 and x of 6, these two, x of 2 and x of 6, and x of 1 and x of 5, x of 1 and x of 5, and finally we're gonna have x of 3 and x of 7, x of 3 and x of 7, which we obtain from the bit reversal, and from the bit reversal. All right, so here this we have G11 of n, which gives G11 of k. So G11 of k, that is DFT of G11 of n, a 2-point DFT of G11. So how to obtain that DFT? It's summation n equals 0 and 1 G11 of n e raised to minus j 2 pi nk on 2, because it's a 2-point DFT. So this will be G11 of k, G11 of k, and still n equal to 0, and expanding for the summation with n equal to 0 and n equal to 1. So n equal to 0, that will be G11 of 0 into this one, n equal to 0 in entire term plus n equal to 1 in entire n, wherever we come across n. So n equal to 0 over here, G11 of 0, n equal to 0 over here, e raised to 0, that will be 1, that is 1, plus n equal to 1 this time, G11 of n equal to 1 this time, G11 of 1 into e raised to minus j 2 pi n equal to 1, it's a 1, k on 2. All right, so this is the expression for G11 of k. So what will be G11 of 0, G11 of 0. So what we have to do is, we have G11 of k, and to obtain that G11 of 0, G11 of 0, wherever we find k, plug in with a 0, that's it. G11 of k we want g11 of 0. What this says is, in the entire expression for g11 of k, wherever we have k, plug in with a 0. So do we have a k over here? No, it's a g11 of 0 plus g11 of 1 e raised to minus j 2 pi, and k is 0. It's a 0 on 2. Now this one will be 1. E raised to entire thing that becomes 0, and this will be 1. This will be 1. G11 of 1. G11 of 1, which is still equal to, what is our G11 of 0, which we established in the beginning while decimating that 8 sequence into 4 and 4 into 2. G11 of 0. G11 of 0. To pick G11 of 0 from the 2 point, it's a F1 of 0 from the 4 point and x of 0 from the 8 point. So G11 of 0, it's a x of 0 plus G11 of 1. G11 of 1, it's a F1 of 2 from the 4 point and x of 4 from the 8 point. It's a x of 4. Now how to show this butterfly structure? Here we're going to have that x of 0 and x of 4, and still another one. It's a 2 point. We have done with the, k also will be running from 0 and 1. Now which gives us G11 of 1. What is that G11 of 1? Wherever we find that k value in this expression for G11 of k, to obtain that G11 of 1, plug in k with 1. So it will be G11 of 0 plus G11 of 1 into e raised to minus j 2 pi, k value is 1, minus j 2 pi on 2. So this gets cancelled. Alright, so we are left with e raised to minus j pi, which is minus 1. How that is minus 1? E raised to minus j pi can be written as cos pi minus j sin pi, and cos pi it's minus 1, minus j sin pi it's a 0. So e raised to minus j pi, which is left over here, this 2 gets cancelled, and now this one is minus 1, this part, this one is minus 1, so we're gonna have that minus over here. Now this is for G11 of 1. So how to show that in a butterfly structure over here? Here we're gonna have that, G11 of 0, G11 of 0 over here, G11 of 1 over here. Alright, so how to represent this one? X of 0 plus x of 4. You already have x of 0 over here and a signal over here which gives x of 0 plus x of 4. So that way, that finishes G11 of 0. This is how. And how to get that G11 of 1? G11 of 1 is over here. How to get that? X of 0 here, x of 0 over here and here with the minus x4, isn't it? G11 of 0 in the sense, yeah guys, G11 of 0 is once again x of 0 minus G11 of 1 is x of 4. How to show this? We have that x of 0 from this side, we have that x of 4 from this side, but with a negative over here, with a minus 1 over here. That gives us G11 of 0 and G11 of 1. So this is how we finish that first. Like this is the procedure to obtain that the butterfly structure for the first stage, and we are done with G11 of 0 and G11 of 1, isn't it? So what about this one? G12 of n gives G12 of k. Alright, G12 of k, which is DFT of G12 of n, 2-point DFT for G12 of n, in the sense summation n equals 0, 1, G12 of n e raised to minus j 2 pi nk on 2. It's a 2-point DFT. Alright, so expanding it with n equal to 0 plus n equal to 1, which gives G12 of k, and here what is that? N equal to 0, so G12 of 0 e raised to 0, n 0, this will be 0, it will be 0, that will be 1 plus this is for n equal to 0 plus n equal to 1, we're going to have g12 of 1 e raised to minus j 2 pi k on 2. So this is for g11 of k. So how to obtain that? g12 of k, g12 of 0, what it says, k is 0, wherever we find k, plug in with the 0. So g12 of 0 plus g12 of 1 into e raised to, if we have a 0 over here, this becomes 0, e raised to 0, that will be 1, and we're gonna have that it's a 1, which is still equal to, as in the beginning we have established a relationship 8 point, 4 point and 2 point. G1, if we are picking G12 of 0, G12 of 0, it's picking up F1 of 1 from the 4 point DFT and X of 2 from the 8 point DFT. So G12 of 0, G12 of 0, which is X of 2, X of 2 plus, what is that, G12 of 1, G12 of 1, we are picking F1 of 3 from the 4 point and X of 6 from the 8 point. It's a X of 6. In the same way, G12 of 1, we're going to have following the same procedure. G12 of 1, plugging in k equal to 1 over here. G12 of 0, we don't have k over here, plus G12 of 1, we have a k over here, which gives e raised to minus j 2 pi, k is 1 on 2, k, it's a 1, so this gets cancelled, and this becomes minus 1, which we did previously, which is equal to G12 of 0 plus minus, we have a minus 1 over here, minus G12 of 1 still, which is X of 2 minus X of 6. Some authors they leave this as where that will be some 2 with a twiddle factor. Even this is okay, X of 2 plus 6. Here we have X of 2 and X of 6, X of 2 over here and X of 6 from this side, which gives us G12 of 0, and with the negative over here, X of 2 minus X of 6, which gives us X of 2 minus X of 6, which gives us G12 of 1, G12 of 1. So this is how we complete the first stage of computation. The same way, go ahead with the rest of that. For G21 of k, G22 of k, the same, you can see the pattern. All right. So from here, x1 of 5 and x of 1 and x of 5, we're gonna have this one. We're gonna have G21 of 0, and with a negative over here, which gives us G21 of 1 with this G2 of 1, and over here with this one we're going to have G22 DFT for this one, G22 of n. So we're going to have G22 of 0 over here with this, and with the negative over here, with the negative in a sense minus over here, we're going to have G22 of 1 with this arrangement, with this butterfly structure, which gives the first stage of computation. All right. And from G11 of k, which will be having that F1 of k, we have G11 of k. Hold on, we are done. If we are done with this computation, the next stage will be very much easier with this equation and with this equation. All right. So recall this one. Actually, we don't need this one once we have established a relationship. Let me hold on. Rewriting that expression for F1 of k. F1 of k, what do we have? F1 of k, where do I have? Yeah, F1 of k. Let me write over here. F1 of k f1 of k. Rewrite this very expression which was written from breaking down the 4 point to 2 point. g11 of k, g11 of k plus g12 of k with the twiddle factor k on 4 with the twiddle factor. Now how to obtain that? f1 of 0, f1 of 0, what it says is wherever you find the k in this expression, plug in with a 0, like k equal to 0, k equal to 0, k equal to 0, k equal to 0. So we're gonna have g11 of 0 plus g12 of 0 with the twiddle factor 0 on 4. And what is that? f1 of 1, what it says, wherever in this expression, wherever we find that k, plug in with 1, which is g11 of 1 plus g12 of 1 with a twiddle factor 1 and 4, 1 over 4. And f1 of 2, which is g11 of 2 plus g12 of 2 with the twiddle factor k is 2 over 4. But do we have g11 of 2 over here? We have g11 of 1, we have g11 of 0, g12 of 0, yeah, we have g12 of 1 we have, but we don't have g11 of 2. So what to do over here? Now here comes, we already have that computation for g11 of 0, g11 of 1, g12 of 0, g12 of 1. So we don't calculate further, but over here we make use of that periodicity property. What that periodicity property says? For the it's like x of k plus n is x of k itself. How to prove this? Yeah, a small proof over here. Let me do it. What is that expression for x of k? X of k is summation n equals 0 to n minus 1 x of n e raised to minus j 2 pi nk on n. Alright. So remember, g11 of k is a 2 point DFT. N equal to 2, it's periodic with a 2. Remember this very much, that we will have to make use of the periodicity property over this one. Alright. So this is the general expression for x of k. Now what if we have x of k plus n, which gives us summation, no change in this one, n equal to 0 to n minus 1, okay. We are not changing the time factor, we are focusing on the frequency factor, e raised to minus j 2 pi n, and k with k plus n number n on n. So which can be no change in the summation, n equals to 0 to n minus 1 x of n. Over here e raised to, splitting into two parts, minus j 2 pi nk on n from this one, this multiple, e raised to minus j 2 pi e raised to minus j 2 pi n on n. Alright. Yeah, e raised to minus j over here, okay. So this one, this n and this n gets cancelled, this n and that n gets cancelled. Alright. So is that e raised to minus j 2 pi nk on k on n. Yeah, it is. Alright. So we don't have this anymore, for any value of n equal to 0, 1, 2, 3, 4, alright, e raised to, what is that, e raised to minus k, yeah, n equal to 0, 1, 2, even pi, yeah, this value is 1 for any value of n. Check it, e raised to e raised to minus j 2 pi if n equal to 1 equal to cos 2 pi minus j sine 2 pi. Yeah, n pi, it's a 1. For any value of n, plug in any value of n over here. This e raised to minus j can be written into Euler's identity and then can be checked, and this value is this entire e raised to minus j 2 pi n is 1 for any value of n, so it's a 1. And where did we come back, guys? This is equal to x of k again. This is equal to x of k again. All right, we started with x of k plus n, we ended with x of k. What it says, if any DFT is periodic with n equal, with the n, it's periodic with n. Now why did I talk about this one over here? If we recall, G11 of k, it's periodic with n equal to 2, capital N equal to 2. So this is very much important over here. G11 this 2 can be written as 0 plus 2 plus G12 of 0 plus 2 with a twiddle factor, no change in that twiddle factor, 2 on 4. Now what it says, now this one, link this one, this part with this part. All right, this half with the, once again with the this half, it's periodic with the 2, with n equal to 2. This DFT is this DFT is periodic with n, so this is written. So even this DFT is periodic with 2, so that can be written as G11 of 0 back to whatever k value here with the n, that k comes over here, plus G12 of 0 with a twiddle factor 2 on 4, making use of that periodicity property, which we have. All right, so in that way, making use of that periodicity property in the butterfly structure. So F1 of 2 is here. Now what about F1 of 3? F1 of 3, which is wherever we have, where it's like G11 of 3 plus G12 of 3 with a twiddle factor 3 over 4. Now this, let me write over here, F1 of 3 can be written as G11 of 1 plus 2, which is very much similar to, now this is k plus n, periodic with n equal to 2, plus G12 of 1 plus 2 with a twiddle factor 3 over 4. Now this is our k and plus these are n, which can be rounded to k only. That is F1 of 3 G11 of 1 plus G12 of 1 with a twiddle factor 3 over 4. Why this much of exercise? We already have G11 of 1, G12 of 1. We already have from this one. G11 of 1 is already calculated, G12 of 1 is already calculated. So why do we go for another? Reducing the complexity, that's it. And what do we have? F1 of 0. F1 of 0 is obtained from F1 of 0, G11 of 0 plus G12 of 0. G11 of 0 is over here, G12 of 0 is over here. So this gives, now this one, 2-point DFT, which gives 4-point DFT. All right. So F1 of 0 over here, what is that? F1 of 0, which is obtained from F1 of 0, which is obtained from G11 of 0, G11 of 0 from this side plus G12 of 0. G12 of 0 is over here. G12 of 0 is over here. All right. G12 of 0 over here with a twiddle factor G12 of 0 with the twiddle factor. Let that twiddle factor be here. That twiddle factor G12 of 0 with the twiddle factor 0 over 4. Alright, so we are done with F1 of 0. F1 of 0 with this one. F1 of 1. F1 of 1. G11 of 1. G1 F1 of 1. F1 of 1. From G11 of 1. G11 of 1 is over here. Plus G12 of 1. G12 of 1 is over here. So we're gonna have that that signal from here. So we're gonna have that from here with the twiddle factor. What twiddle factor do we have? We are calculating for F1 of 1 with the twiddle factor 1 over 4 with the twiddle factor 1 over 4. So we are done with F1 of 1. F1 of 1. So F1 of 2. F1 of 2. It's a G11 of 0. G11 of 0 plus G12 of 0. Here G11 of 0. G11 of 0 is over here. Alright guys, some authors suggest something else over here. Some authors suggest something else over here. This twiddle factor. Alright, we're gonna have a negative over here, which gives a negative over here, -1 and -1 over here. Even this is okay, the same results. Let me explain for 1 to save the time. You do the computation. Like we can leave it over here, but there is some other suggestion. Like what is that twiddle factor, guys? Twiddle factor 2 on 4. What it is? E raised to minus j 2 pi. E raised to minus j for the twiddle factor 2 over 4, which is e raised to minus j pi. Alright, minus j pi. Why? Because 2 and 4 gets cancelled, and this one will be -1. On the other hand, why? Because we have that 0 over 4. What is that twiddle factor 0 over 4? It is e raised to minus j 2 pi, that twiddle factor, into 0 over 4, that will be e raised to 0, that will be 1. Alright, so the same one, that 1, this one, not -1, I'm talking about the 1, I'm talking about 1. So negative, it's okay, that 1 is 1. So in the place of 1, in the place of this one, okay, negative, okay, in the place of 1, we're gonna write twiddle factor 0 over 4. In the sense F1 of 2 will have this negative will appear over, I mean this one, this twiddle factor with 2 over 4 can be written as 0 over 4, and that negative comes over here, and this is okay if we don't, it's very much okay, the result will be same during the numericals if we don't do this. We did this because we already have that twiddle factor 0 over 4, while simulation we have to reduce the complexity, and so we already have 0 over 4. Why to obtain that 2 over 4? Because we already have that 0 over 4, so go for negative over here. And then where is that F1 of 2? F1 of 2 is written over here. F1 of 2 is written over here with, what is that? G11 of 0, G11 of 0 from here, this side, G11 of 0 from here, and so what if we don't need another twiddle factor over here? Let's write this twiddle factor here itself with the 0 over here. This flows this side also, and with the negative over here, we will finish G11 of 2 minus G11 of 2 with the twiddle factor over here. This is the concept over here. Why to write why to make it more complexity with another twiddle factors, they say. Alright, okay, even if we, okay, this, even we don't need to change this one, the result will be same while we do the numericals. And what about F1 of 3? F1 of 3 is, F1 of 3, even if we leave that like twiddle factor with a 2 over 4, the same result. Okay, don't worry. Why? Because I need to save the time, and so I'll be not replacing this one. We have all negatives over here, negative over here and here. It's while changing the twiddle factor. Yeah, we're changing the twiddle factor, like 3-4 authors with a different approach, but following the same, like the result will be same. And f1 of 2, we are done with the f1 of 2, which is this one with the twiddle factor. All right, so leave it as it is, or else change that one. That isn't a problem. f1 of 3, we're gonna have that f1 of 3 over here, which is g11 of 1. And now this one twiddle factor, this twiddle factor 3 over 4, that will be minus of twiddle factor 1 over 4. And so this negative comes here with the twiddle factor, that is followed by some other authors. And Anand Kumar, I have taken that from Anand Kumar, he has left as it is, and no problem, that isn't a problem. f1 of 3, g11 of 1 comes from here, this one, g11 of 1 comes from here, this side. And that twiddle factor, because if we have that twiddle factor over here with a negative over here, it is saving. All right, with the twiddle factor and with the twiddle factor 3 over 4. All right, with the twiddle factor 3 over 4. We don't have negative over here, it's simply adding over here. If we had a negative over here, then we would have gone for -1 over here. So it's a positive, and the result will be same. Why? Because it's a periodic. The twiddle factor, the phase will be changing, the magnitude is same. The twiddle factor, this is how finishing. If we had a negative over here, then we would the same thing, by changing the twiddle factor we would have imposed that -1, but a twiddle factor is coming from this side, a twiddle factor is coming from this side. All right, so we are done with the f1 of 3 also over here, making use of that periodicity property. And the second half, 2 point, 2 point, 2 point, 2 point, and 4 point, and 4 point, and finally the 8 point. f2 of k, f2 of k, how to obtain that? f2 of 0, what it says, k is 0, wherever you find k, plug in with 0. g21 of 0 plus g22 of 0 with the twiddle factor 0 over 4. So where is that? We're gonna have that f2 of 0 over here. g2 of 0 we already have here, and g2 of g21 of 0 plus g22 of 0, g22 of 0, g22 of 0 all the way comes from here, finishing that with the twiddle factor. Where do we have the twiddle factor? Here we're going to have that twiddle factor 0 over 4, 0 over 4. And what about f2 of 1? We're going to have g21 of 1 plus g22 of 1 with the twiddle factor 1 over 4. All right, so we're going to have f2 of 1 over here, f2 of 1 over here, and which is obtained from g2 of 1 plus g22 of 1. Here we're going to have that g22 of 1, here is that g22 of 1 with the twiddle factor 1 over 4, with the twiddle factor 1 over 4. And what about f2 of 2, g22 of 2 plus we're gonna have that f2 of 2 from g21 of 2 plus g22 of 2 with the twiddle factor 2 of 4, but we don't have g21 of 2, it's only zeros and ones. So what we have to do over here, f of 2 is making use of the periodicity property. g2 of 1 can be written as g2 of 1 0 plus 2. It's a g22 of k is a 2-point DFT with being periodic with n equal to 2 plus g22 of 0 plus 2 with the twiddle factor 2 over 4. Twiddle factor 2 over 4 is equal to minus of twiddle factor 1 over 4. Check it. And so now this one is a k plus n, k plus n, this is k plus n, periodic with n equal to 2, so that can be written as G21 of 0 plus G22 of 0 with the twiddle factor 2 over 4. How to get this one? F2 of 3, sorry, F2 of 2, we are going for F2 of 2. G21 of 0, G21 of 0 comes from here, this G21 of 0 here, and G22 of 0, G22 of 0 already is here with the twiddle factor 2 over 4, which gives F2 of 2. And in the same way we are done with all these F. So what about F2 of 3, which gives us G21 of 3 plus G22 of 3 with the twiddle factor 3 over 4. G21, 3 can be written as 1 plus 2 plus G22, 3 can be written as 1 plus 2 with the twiddle factor 3 over 4, that is F2 of 3, G2 of 1 plus G22 of 1 with the twiddle factor 3 over 4. Why? Because it's periodic, it's a G21 of k, it's a 2-point DFT being periodic with n equal to 2, and according to periodicity property it's like k plus n gets back to k, it's k plus n which gets back to k. And we're going to have that F2 of 3 over here, F2 of 3 over here, which is, guys, where is that? This one from G2 of 1, because of that periodicity property, G2 of 1 from this side, and also that G22 of 1 was here, G22 from here with the twiddle factor 3 over 4, 2 over 4, 1 over 4, yeah, 1 over 4, 0 even, and 1 over, yes, it is 0, 1, and yes, it is. Okay, we don't need to change that one, let the twiddle factor be carried. Yeah, some authors change it, some authors don't change it. The result will be same while we go for the calculation. And for the final stage, we have to consider this expression for getting that final stage of computation, the third stage, the second stage, I mean first stage, second stage, and the third stage, making use of this expression. To get that x of 0, what it says, wherever we find k, plug in with 0, f1 of 0 plus f2 of 0 with the twiddle factor 0 over 8. So f1 of 0 is from here, all right, and f2 of 0, where is that f2 of 0? From here. We have f2 of 0 from here, and a signal from joining these two, will give us x of 0, which gives us x of 0. And how about x of 1? X of 1 will be f1 of 1 plus f2 of 1 with the twiddle factor 1 over 8. Where do we have that f1 of 1? Here, this one, and f2 of 1 over here. All right, so a signal from this to this with a twiddle factor. Guys, where is that? This one, this f2 of 0, isn't it? So we're going to have that twiddle factor 0 over 8. It's a 8, 0 over 8. And f1 of 1 plus f2 of 1 plus f2 of 1, and we're gonna have that twiddle factor 1 over 8 over here. And x of 2 is x of 2, f1 of 2, it's a f1 of 2 plus f2 of 2 with a twiddle factor 2 over 8. F1 of 2 is here, yeah, we have that x of 1 over here, and f1 of 2, it's from here, this side, and f2 of 2 from this side here, and joining these two with the twiddle factor 2 over 8 will give us x of 2. all right, x of 2 and x of 3, which gives us f1 of 3 plus f2 of 3 with the twiddle factor 3 over 8, and here f1 of 3 is over here and f2 of 3 is over here, these two, and with the twiddle factor 3 over 8 will give us, joining these two will give us x of 3, breaking it down. All right, now the actual discussion comes over here, which we already discussed, making use of that periodicity property. X of 4, which is f1 of 4 plus f2 of 4 with the twiddle factor 4 over 8. Guys, do we have f1 of 4? No. f2 of 4? No. So making use of that periodicity property, f1 of k is a 4-point DFT. If you remember, f1 of k is a 4-point DFT which is periodic with n equal to 4, making use of that same property. X of 4, now f1 of 4 can be written as 0 plus 4 plus f2 of 0 plus 4 with the same twiddle factor 4 over 8, or else can be negative with the existing twiddle factor. That isn't a problem at all. So now, which is very much similar to x of k plus n, here match this one, k n plus x of k plus n with the same twiddle factor 4 over 8. So if it is periodic with this, what did we have? X of k, isn't it? So this was x of k plus x of k with that twiddle factor. What is k here? The 0 is k over here, which is f1 of 0 plus f2 of 0 with the twiddle factor 4 over 8, or else there is that will be minus twiddle factor 1 over 8, whatever, 0 over 8 it may be, check it. So we are going for x of 4, f1 of 0 from this side, all right, f1 of 0 from this side, and f2 of 0 from this side, f1 of 0 and f2 of 0, and from this side we're gonna have that twiddle factor over here, which is 4 over 8, and this sum will give us x of 4. This will give us x of 4. In the same way, making use of that periodicity property, we already have the calculation for this one. We don't need to go for f1 of 4, f1 of 5, etc. So x of 5 is f1 of 5 plus f2 of 5 with the twiddle factor 5 over 8, which can be written as, it's a 4-point DFT which is periodic with n equal to 4. f1 of 1 plus 4 plus f2 of 1 plus 4 with a twiddle factor 5 over 8, and so that periodicity property, f1 of 1 plus f2 of 1 with a twiddle factor 5 over 8. Where is that f1 of 1? Here, f1 of 1 from this side and f2 of 1 from this side, joining these two, and with the twiddle factor 5 over 8, which gives us x of 5 over here, the twiddle factor, if I'm not wrong. All right, in the same way, x of 6, that will be f1 of 6 plus f2 of 6 with the twiddle factor 6 over 8. X of 6, it's a periodic with 4-point n equal to 4, so f1 2 plus 4 plus f2 of 2 plus 4 with the twiddle factor 6 of 8. Maybe a change in the third twiddle factor with a negative, that isn't a problem, which is f1 of 2 according to that periodicity property. f2 of 2 with a twiddle factor 6/8, with a twiddle factor 6/8. We are doing for x of 6 over here. f1 of 2, where is that f1 of 2? From here, f1 of 2 from here and all the way connecting to f2 of 2, and with the twiddle factor 6/8, which gives us x of 6, making use of that periodicity property. Even there is a change in the twiddle factor with the negative over here, check it with already existing twiddle factors. And x of 7, you can do it. All right, f1 of 3, joining f2 of 3 and giving a twiddle factor 7/8, which gives us x of 7. That's it. Yeah, it's connected. All these are connected. All right, all these are connected. That radix to DIT FFT for n equal to 8. That's it.